Hi! I hope you're ready to do calculus because that's what we're going to do. Woo woo! Calculus! Yeah! Let's do this thing. Today we're going to talk about particle motion. If you took physics, this should be familiar to you. If you didn't, you'll figure it out very quickly. So we're going to be talking about very boring particles. Our particles move like, think about a little speck, like Horton Hears a Who kind of speck. There's a speck, except those particles are way more interesting. Because, you know, they do things like talk to elephants and save their town and all of that. Oh man, I'm digressing already. It's okay, we can do this thing. These particles are very boring. They either move on the x-axis or the y-axis, and most likely it's going to be the x-axis. So we're talking about horizontal or vertical movement. Very boring. We are going to be dealing with position, velocity, or acceleration, sometimes equations, sometimes graphs, sometimes tables. Woo woo! Of a particle's motion are defined by functions, but the particle does not move along the graph of the function. So let's say I've got a position function that looks like this. Position. That does not mean the particle is on a little roller coaster. You'll see what this means. Again, particles are very boring. They move right or left or up or down, and that's it. And they can't do so at the same time. And this one, most of the time that we're talking about it, we're talking along the x-axis. Rarely it'll be along the y-axis, but mainly particles move left or right. Okay, so we'll talk about this later too in Unit 6 and 7 once we get into integrals. So calculus is divided into 3 parts. There are limits, which is a little part. Then we've got derivatives and then integrals. And derivatives are a slope of tangent, and then integrals are if we take the slope, we go back and find the original function. Fun times. I feel like I just gave away the ending of a good book. There's so much more for you to know though, so we're good. Okay, so let's get into this. Average and instantaneous velocity. So if I want to find the velocity of the function, average velocity, velocity is a rate of change. Think about it where you've got like miles per hour is a velocity. A velocity has a direction. So if velocity is positive, we're going to talk about it in a little bit, but it has direction. We can know which way the particle is moving. We've got an object over time. So we've got this time from A to B, time A to time B. And if I want the velocity average, I take the displacement divided by the travel time. Or I can say whatever my position is, my original function of position, I can say P of B minus P of A over B minus A. The reason for this is, let's say this is my position function. And I was saying that this is, I don't know, let's say meters. I know it's a little hard to see, but meters on the y-axis, second down here. If I were to take the slope of this line, say, let's even say from A to B, so from here to here, and I was to take the slope of that line, I would be finding an average rate of change over meters per second, because P of B minus P of A would be meters. B minus A is just my time, seconds, and I'm given velocity. So you take the average rate of change of position. This is where I get average velocity. Instantaneous velocity is a little bit different. Instantaneous rate of change is just the derivative. It's the slope of the tangent. This is the slope of the secant for average velocity. Instantaneous velocity is instantaneous rate of change, also known as the derivative. So this would be P prime of t. The derivative is a moment in time. It's the velocity, or I can say the instantaneous rate of change, instantaneous velocity, P prime of t. Oh man, this is all stuff that you knew before, but now we're just saying it in a new way. Yay! Okay, so here I've got particle's position, and it's given by this function, P of t, where P of t is measured in centimeters and t is measured in seconds. Okay, what is the average velocity? So if I'm thinking velocity, and velocity, like a common measurement for velocity is like meters per second. It's a distance over a time. Here I've got centimeters over seconds. This would be like rise over run if I have a graph of P of t. And I've got centimeters on the y-axis. And I've got seconds on the x-axis and I take the slope of that line, the slope of that line would be centimeters over seconds velocity. So average velocity from 1 to 3 seconds is going to be p of 3 minus p of 1. That's also the change in distance. Like if I'm at position 3, position 1, and I subtract them, that'd be the displacement over my time. This is only two seconds. To find this answer, where's my calculator? You can go to y equals, you could do this in your home screen, but I put in this function for position, so e to the x power sine of x, and then I graph it, and I can use second, calculate the value, and then it's going to come up with the x equals. I'm going to say x equals 3, and I see 2.8344711. Keep as many places after the decimal as you can until your final answer, and then you can round to 3 places after the decimal. So this would be 2.8344711 minus, in the denominator I know 3 minus 1 is 2. P of 1, second, calculate my value, and I get 2.2873553. And then you just keep rolling. I'm going to go back to the home screen. So 2.8344711 minus 2.2873553. I divided that answer by 2. I got 0.273. And this is where this is my final answer. So I could just leave it like that. Or I could round it and say 0.274. But I have to indicate units of measure. And this is where you go back, and this is a good way to check yourself anyway, to make sure that you have the right setup initially. Position was measured in centimeters. This time, 3 minus 1, was my seconds. You do not have to put both of these answers, choose one. My final answer is 0.273 centimeters per second. That's the average velocity from time 1 to time 3. Instantaneous velocity, instantaneous rate of change. If I say instantaneous rate of change, you think derivative, or you might have said slope of the tangent, because that's the same thing. Instantaneous velocity is going to be at a moment. So if I have this p of t and I still want the rate of change, p prime of 1.5. We could take the derivative just for good fun. I think we're actually going to need it in a little bit. So just to remember it, p prime of t. We do the product rule. What's the product rule? First, the derivative of the second, the derivative of sine is cosine, plus the second times the derivative of the first. The derivative of e to the t is just e to the t. So you could do this and then substitute in 1.5 to your calculator. Or just to remember, the other way that we could do this is if I go to my graph, I've already got this original function of p of x in there. If I say second, calculate, and I go down to dy dx, that's my derivative, it looks like nothing happened. But if I just start typing 1.5, ta-da, I get 4.787. And I could keep going, 4831, but this is my final answer, so I'm fine to stop there. And then it says indicate units of measure, really important. So this is where you have to think through what was I actually finding. This is p prime of 1.5. This is the instantaneous rate of change at time 1.5 seconds. This would be the slope of my position. Think about rise over run, centimeters per second. Does that make sense for instantaneous velocity for you? I would think so. I can also put over here, this is v of 1.5. So the derivative of position is velocity. The rate of change of position is velocity. Let's do more. We're on to page 138. So before we proceed, a connection needs to be made. When we're given a function f of x, how did we find the slope of the secant line? Okay, so if you have a function f and you want to find the slope of the secant line from a to b, how'd you do that? Do we have so much in common? Did we get the same thing? F of b minus f of a over b minus a. This is the slope of the secant line. In terms of the position of the particle, what does this correspond to? So if you were to find the particle, f of b minus a, or p of b minus p of a over b minus a, what is that? This is the average velocity. If I find, and this was the slope of the secant. If you want instantaneous velocity, there's another one. Instantaneous velocity. Like before, we would have found just f prime. This is really close. It's just p prime. We did it. Okay, let's do more. So what about acceleration? Let's think through this a little bit. If I want to find the average acceleration over an interval a to b, so this is over a time period. It's not in a moment, this is over an interval. So you're thinking slope of the secant again. But what graph do we use this time? Think about acceleration. The most common thing, the units used for acceleration would be meters per second squared. What does that mean? So meters per second squared is commonly used. If you took physics, you would see that a lot. I'm going to tell you another way that you can write that is meters per second. What is measured in meters per second? Like what's something that could be? Velocity. So velocity would be v of b minus v of a. That would give you the meters per second over seconds. What? Average acceleration is just the slope of the secant of velocity? That was a big deal. So this is the average acceleration, slope of the secant of velocity. So still slope of the secant. Every time we've got an average velocity, think slope of the secant. Every time we've got instantaneous velocity or acceleration or whatever this is, I think I'm going to set this wrong. Average acceleration is the slope of the secant of velocity. There we go. We got it. V of b minus v of a, because that would give you the meters per second or some distance per time. B minus a would give you some unit of time, like seconds down here. Instantaneous acceleration, just like for velocity, we were able to take the derivative of position, because it's a rate of change at a moment of position. Here, same idea. You can take the derivative of velocity. That will give you the rate of change at a moment. Let's do one more connection now. If a of t, acceleration, is the derivative of velocity, what was velocity the derivative of? Position. But hold on, that doesn't make sense right now because this is v prime of t. Acceleration, so if I go backwards, so let's say here, if I have position and I took the derivative of, I get velocity. If I take the derivative of that, I get acceleration. I'm going to say that a bunch more times. But if I'm thinking about it this way, an acceleration is the derivative of velocity, it must be the second derivative of position. So all those things you learned before about a function increasing, decreasing, position being positive or negative, and the original function and the points of inflection, all super important right here. I know some of you are groaning and some of you are happy, but this is a good chance to solidify your understanding and help you really, really get this. I'm convinced that you can. Okay, so we've got this particle's position, so the same thing as on the last page, where p of t is measured in centimeters and t is measured in seconds. If I want the average acceleration, acceleration would not be, so let's say if this is P of t, I've got centimeters over here and seconds over here, and I took the slope of that line. I guess I could actually do the real graph because we know what it looks like, but whatever. If I took the slope of this line, I would just get centimeters per second. That's only velocity. It's not enough. If I had a graph of velocity though, this would be centimeters per second on the y-axis. Down here I'd have seconds. So if I took the slope of this line, obviously I'm making this up because the real graph of P of t actually looks like this. So if I take velocity and I've got centimeters per second on the y-axis, seconds down here, if I take the slope of this line, think about it, rise over run, I have centimeters per second. That gives me my units for acceleration. So we're good. So we should be thinking about this graph now, velocity. Average, as soon as you're seeing average acceleration, average rate of change, you should be thinking slope of the secant, but this time for velocity. You might be thinking, how exactly do I do that? You could do this a couple ways. You could go, because this was a graph of position, you could find the derivative at 3, and you could find this value. You could, sorry, I'm just looking. Yeah, you could find the derivative at 3, the derivative at 1, because that would give you velocity at 3, velocity at 1. Or we could go back and say, you know what, on the previous page, we found the other derivative. Where was that page? Here it is, coming back. We found P prime of t, which would also be known as V of t. And so I would get e to the x power cosine of x plus sine of x, and then e to the x power. So, and I turned off the first one, I highlighted the equal sign and then clicked on it so that it wouldn't graph that anymore. Now I've got the graph of velocity, and I think the velocity at 3 was like -17 something, so just so you trust me, let's check. If I calculate the value at 3, hey, we know we're right because we get the same thing here. So, velocity at 3. Trying to see how can I show you this and this at the same time. There we go. It's a little bit strange, but that'd be -17.05006 minus the velocity at 1. You find that. 3.75604992. 3 minus 1 is 2. -17.05006 minus 3.7560492. I'm going to divide this by 2 right now. I get -10.403. So now I can take this to 3 places after the decimal. I have to indicate appropriate units of measure, and you should actually do this at the beginning and at the end. So just to test to make sure that you're using the right graph, because the most common mistake is just to say, well, I know this is the slope of the secant, but then choosing position instead of velocity to find that slope of the secant. So here, velocity was given in centimeters per second. 3 minus 1, this was just my seconds. It's my unit of time. So centimeters per second, does that make sense for acceleration? Yes, I'm good. So this is my average acceleration from 1 to 3 seconds. It was the slope of the secant line. If I went instantaneous acceleration, instantaneous rate of change is the derivative. But the tricky part is figuring out the derivative of what? Acceleration is the derivative of velocity. And to test that, to make sure that I'm right, I just have to think through this graph and think, okay, if I did rise over run, centimeters per second, would that give me acceleration? Yes. So what I want to find is the derivative of velocity at time 1.5, because that would give me the acceleration at 1.5. And yes, it would also give me the second derivative of the position, but there's no way for me to do that on my calculator. There is no need to take the derivative of y2, because you would have to do the product rule twice. You'd end up using your calculator anyway, and while it might be good fun and you would gain a lot of friends, oops, sorry, I still want just this is the graph of velocity. If you go to the graph, and then you wait patiently. If I click on second, calc, and go down to dy dx, this means I'm finding the derivative of velocity, which is the same thing as acceleration. It looks like you can't do anything, but you can just start typing 1.5. And I get 0.634. And then this one, sorry, ooh, good, we're good, would be, you can write centimeters per second if you wanted to, because you're thinking through this whole process and you know it's like a rate of a rate. That's what acceleration is. Or you can write centimeters per second squared, but it's really important that you indicate units, even though this one doesn't say it. Super important, indicate units if they're given to you originally. If they're not, then don't. Okay, last thing, let's connect this all together. In this one, we're going to say position, velocity, and acceleration. And I do this a lot when I'm talking about it, and you'll see why, but I go position, velocity, acceleration. I can tell, like, I make the hand gestures, but also I just say that a lot and think about it in my head, position, then velocity, and acceleration. So if position corresponds with p of t, so this is just my original function. Sometimes this is s of t. I actually had it written like that before, but I changed it because s's sometimes look like 5 when you write them too much. But sometimes this is s of t. Sometimes it's kind of confusing. It will be x of t, which isn't my favorite, but they'll write x of t because the particle's only moving in the x-axis. But you're given a function. This could also be f of x. You're given a function. Velocity is the derivative of position. Acceleration is the derivative of velocity, and also the second derivative of position. So I'm thinking position, I take the derivative, I get velocity, I take the derivative of that, and I get acceleration. So you can see p, p prime, p double prime, v, v prime, works. Okay, so then we'll just say, like, so now we're making the connections between all these things. So velocity. Velocity is greater than 0, or I could say velocity is positive. Let's think about this. Velocity is the derivative of position. What happened when the derivative is positive? What happens to the function? Normally we say the function is increasing, or the position is increasing. Here, because these particles are very boring, we're just going to go, I could say moving up or moving right. I'm just going to go to the right. If velocity is positive, the position is increasing, or I can say moving to the right. Think about a number line. If you were increasing, you're going to the positive numbers, positive way, to the right. If velocity is negative, or I can say the derivative of position is negative, that means the function that it's the derivative of, in this case position, is decreasing. So which way? Moving left. So that's the only new part of this. So still the same connections that you made in the last unit you're making here, just moving right, moving left is the new part. Changing from positive to negative. So think about this. Positive to negative would mean on the graph position increasing to decreasing, also known as a relative maximum. Or you could say that this particle is moving right. So changing directions right to left. But all those same things apply. What about negative to positive? Decreasing to increasing, which will show up as a relative min. And again, changing directions left to right. If we've got 0 or undefined, this is where we've got a possible change in directions. Min or max. I should say possible relative min or max. Okay, let's think about this now. If we've got acceleration, and this would look different depending on if this over here, if this was position, this would look different. But we've got acceleration, and acceleration is the derivative of velocity. So think about this. We've got acceleration, and again, I'm going to skip the 0 undefined, come back to it. If I've got acceleration is positive or greater than 0, what do you think that means about velocity? Well, I don't even know why I'm writing velocity. I don't want to get in the habit. That means velocity is increasing. If acceleration is negative, that means velocity is decreasing. Changing from positive to negative, so we're changing velocity, would be changing increasing to decreasing. There's a relative max. So nothing really new here. It's just knowing that the derivative of velocity is acceleration. Negative to positive, relative min. And this one is a possible relative min or max. I wouldn't quite say easy peasy lemon squeezy, but I don't know if it's quite difficult, lemon difficult, besides the fact that there's a lot to keep in your head. So I guess I would say that some of this is difficult, lemon difficult, but I don't know some common saying for that you're really smart, but you're really smart, or you wouldn't be here. You wouldn't have done well enough in math classes to get to this point. And so there is no reason that you can't do well now. Please reach out if you need anything at all. Let me know if you need help with this. Some of this stuff, like, it's hard to get this in your head, and after we come back from break, or if you're even off on a weekend or something else, like, some of this is difficult to retain. So please let me know if you need any help at all, and I'll help you. Thanks. I appreciate you. Bye.